Are we live?
We are live.
Nice.
Hi, everyone. Thanks for joining us today. We are going to talk about a topic that is very close to my heart as a former or recovering physicist. We're going to talk about symmetries and deep learning and all of those good things. And topic we brought in my good friend Nima and our co-host Serena. So maybe I'll ask Nima to quickly introduce himself. Tell us what's your story.
Hello, everyone. I'm Nima Dehmami. I'm also a physicist. Like Amir, we went to the same master's program back in Iran. And so I started working on complex systems during my PhD and then switched to machine learning later. And now I'm a researcher at IBM, focusing mostly on machine learning for scientific applications.
That's great. And Serena, what's new with you?
Not too much is new, really. I have been seeing more growth on my Instagram. For those of you who might not be familiar, I'm developing an app called Food Shake, which lets you make any recipe into a plant-based one. And I have a TikTok that's been growing very successfully. And in recent months, I joined Instagram. And it's very different to grow on Instagram as it is on TikTok, different to grow on YouTube, but finally starting to figure it out. But yeah, check me out on social media. Friendly Veg.
Friendly Veg, okay.
Yeah.
There you go. So, and is it, so you're essentially allowing people to create or, have more plant-based diets? Is that the idea?
Exactly. More variety. And the idea is if you want to eat something that's plant-based, maybe you want to eat something familiar, so you can put in one of your existing recipes and it'll output the closest plant-based version for you. No compromise in taste, ideally.
Yeah. Does it preserve the symmetries in the recipe?
You could say it sort of preserves the symmetries.
Huh.
Great segue.
Interesting. There you go. There you go. What are you all drinking? Oh, where did I put my water? Okay, I forgot my water somewhere.
Yeah.
I've got water as well. Yeah.
Yeah, old-fashioned H2O. So
sounds good. So maybe I'll up off and then pass it on to Serena. So the first time I came across symmetry, well, I probably noticed the first round thing. Sorry, I meant in a more professional setting was when in physics I took group theory. I think in a more formalized sense, I started saying, oh, okay, so these things around, they have symmetries. And then I started learning about all the other types of symmetries. And I think what was, took me a minute to learn, but was very satisfying to learn was the reason that we love symmetries in physics is that it allows us to grab a problem and use the symmetries to parameterize the problem in a way that with very, very the most general theory about that problem. We do have this, I guess, canonical joke that we, approximate, as a spherical cows. And to some extent, that's the same idea. Like we like the sphere's symmetry and we want to use it to, simplify the problem. So in my mind, I ended up associating symmetries and understanding them and leveraging them in describing systems as a way to simplify the problems so that they can generate with fewer parameters. Is that how you understand symmetries too? Or is that too nerdy to start it? But yeah.
No, actually, that's how I think about symmetries now. It was not how I initially heard about them, which was, I feel, sometime during high school, I was just curious about more advanced physics, and I was just reading random stuff hearing the word like standard models, symmetry groups, things like that. I had no idea what these things are. I would see these things like SU2 and stuff like that, but I had no idea what those things were until, a few years later in college. Once I also took group theory, that's when I first started learning what those things meant. And it took me much longer, maybe, like until just recently, to appreciate the importance of it in helping us build simpler models and have a very compact model with very few parameters that allows you to describe the behavior of a system.
Well,
and now Go ahead.
hearing these two physicists just makes me think of this quote from a paper that Amir shared with me. The paper is Machine Learning Hidden Symmetries. And yeah, apparently Philip Anderson, who I learned is a famous physicist, I'm sure you two both know of
Yes.
who Philip was. Philip said that it's only slightly overstating the case to say that physics is the study of symmetry. So yeah, hearing you two talk about that really makes me think of that. I was wondering, what's a more like explain like I'm 5 or explain like I haven't actually studied physics and math for many, many years definition of symmetry? Because I think we all know about symmetry, like in terms of faces. People who have a more symmetrical face, so it looks the same on the right as it looks on the left, are typically more conventionally beautiful. So can we use any sort of definition like that for the mathematical term?
Maybe I'll take a stab at it to, give it more, and Nima can definitely get the more correct and in-depth version. So to me, it always goes back to how many parameters do I need to describe a system. Like, if there are many symmetries in a system, you could describe it like a circle symmetry. So I only need one parameter to describe it, right? Like it is essentially the circumference of the circle. And that's all the information I need to know, and the fact that the system has rotational symmetry to describe it. While, an ellipse, has a slide, right? Like I need two parameters to describe it. Or translational symmetry. Like if I see something that is happening in this portion of a land, and if I know the country, I know that if I move 10 feet over, the same thing is going to happen, right? So for example, gravitational force on the surface of Earth, if you experience it at a location and then translate 10 feet over, experience the same thing. So the fact that you're standing here or there is not, that's a symmetric parameter that is, leaves the example, and therefore, the experience is going to be the same. Is that
so? I wanna refine that a little bit, because I think what you are mentioning is something philosophical also about an assumption that goes into physics. When we say it's theory that has a symmetry, then it is what you just described. But let me take one step further back. But just like you said that you need fewer parameters to describe it. So what you said, Serena, about a face being symmetrical. So that would mean that the right half looks the same as the left half if you do a mirror symmetry and transform them into the mirror image. So because of that, you don't need to have the whole face to describe the face. You can only work with just half of the face. That's enough to describe. So it's reducing the amount of information required to describe a system. But in general, we say a system has a symmetry if there is some change that you can do to some part of it to give you another part of it, or basically transform it to itself by some change. For example, in a circle, you can rotate the circle and it still looks like a circle and it goes back to itself. So you can have discrete symmetries. Let's say you have a pentagon. If you rotate it by a fifth of a full rotation, it goes back to itself. So that would be the mathematical property of having symmetry. But something else that's very interesting that Amir mentioned, and that goes at the heart of how physicists use symmetry and how machine learning also uses symmetry, is the assumption that a system is symmetrical if doing certain transformations on the system give you the same system's behavior. So, for example, the train example that Amir mentioned. Let's say you expect certain behavior from physics inside the train when it is here in Boston, for example. If you assume that your objects behave the same way, even when the train goes down to DC, then you are assuming that the physical world that was out there had a symmetry. And that symmetry was, when you shift objects, the laws of physics did not change. That shift symmetry is called translational symmetry.
So in
I
that
think
train, yeah, in that train example, is that symmetry you're talking about symmetry of the sort of the whatever's happening inside the train? So it's specific to the train, or is it a symmetry of the overall world, like external to the train?
It really depends on that depends on the scope of the hypothesis that you're putting out. If you may make a conservative assumption and say, all the observations I'm making are within this train, so I will hypothesize that the laws of physics inside the train are invariant, meaning they don't change under translations. So when some laws do not change, when some laws are invariant under a transformation, we say that that system or that theory that is describing those laws, that theory has this kind of symmetry.
Right. I think the few examples that we talked about are more focused on a static symmetry, like essentially, a symmetric face is an object that has sort of a static symmetry. But you can also talk about symmetry when you're dynamics in systems, right? For example, the gravitational example that I gave, that's essentially the way a ball would fall here and the way a ball would fall 10 feet from here is going to be the same because there is, because gravity as a force and the dynamic that it creates has translational symmetry. Like if you move laterally, it's not going to change. But if you move vertically, that will change because it doesn't have that symmetry. So in general, I think about both, but really the more interesting one is the dynamic, because the symmetry, like taking into account symmetries of problems when you're talking about their dynamics, means that you can parameterize the behavior of the system without necessarily seeing it. Sort of like if I know a ball falls in a specific way here, I'll be able to predict how it will fall over there. And that generalization of information, like the way if I have two pieces of information, which is half of your face and the fact that your face is symmetrical, I don't need to be able to predict where your eye is on the other side of your face. So that ability, predictability, I think is one of the most important reasons that physicists love symmetry, because it just is so powerful. Like you just need to know, these are the symmetries I have in my problem, and these are the general, dynamics that governs it. Then I can apply it in a lot of then you can do counterfactual reasoning. Like you can say, I'm not on a very good guess that a ball is going to analyze in this specific way.
Mm-hmm. Yeah, that's how we designed the rovers and everything. But I think it's also worth mentioning that a lot of the symmetries that we just described were approximate symmetries, right? Like gravity doesn't have translation symmetry like we described, but on short distances, because the Earth kind of looks flat. I mean, the Earth is not flat, but just on short distances. That's why it looks like a translation symmetry, whereas in reality, it was actually a rotational symmetry, because you were moving on this sphere that was Earth, and that showed itself as a translation, even though it was a rotational symmetry. Yeah, I think just to summarize, I feel the most important point was that we can use it in physics to reduce the amount of parameters that we need to describe a system. And recently, this idea has also gained a lot of traction in machine learning. Yeah.
And it feels to me that this matters mostly in computer vision.
So a lot of people, so I have some personal opinions here. Please don't think that this is, this is just my personal opinion. I feel you see a lot of it in computer vision because a lot of the work in a big chunk of machine learning is dominated by computer vision. Of course, now there's a lot of different directions, but computer vision is sort of a good playground for testing a lot of things because it doesn't have a huge barrier of entry. You can just take one of those standard benchmarks and start testing on it. So a lot of results that you see are in computer vision, but that doesn't mean that the concept is only important in computer vision. In fact, there is a lot of uses of symmetries in machine learning in problems that are scientific, such as solving turbulence, basically predicting the next frame in a system that is turbulent, or using the symmetries to reduce the search space for building molecules. Let's say, each component of your molecule has to have a specific symmetry. So there's a lot of scientific applications, actually.
So one of the things that I think, but I don't have a lot of knowledge about, is the relationship between symmetries and topology. I've heard of this term, topological data analysis. Is there any relationship between what we are talking about and that?
Yeah, go ahead.
And maybe for a more specific example, a while ago, well, that's 3 years ago, we had a talk that talked about the topology of how deep learning works. And the details of the talk, but essentially, I'm sure you're familiar with the concept of embeddings, but essentially a lot of deep learning techniques learn embeddings of entities that we are interested in, right? And paper claimed was that essentially what embedding is identifying topology, what manifold sits in originally, and that's probably a very sparse space that the data is sitting on. And then essentially representation learning is creating this mapping from that topology, that manifold, to a manifold that is lower dimensional, but captures the most of the original manifold. Like essentially reduces it to a manifold that is lower dimensional, but has all the important, I guess, in the original data set. Is this related?
So I think there's two things. I think they can be independent, actually, or they can be related. So you can, let's say there is this classic problem that people use as one of the small benchmarks in machine learning, which is a spiral of basically two spirals that are intertwined with each other, and you're trying to classify to which spiral a particular point belongs. And you can think of that as like, the actual manifold on which the data is living is very low dimensional. In this case, it's one dimensional. It's just one spiral, and then there's another spiral. Technically, in 2 dimensions, you could be, once you flatten out this spiral, and, all the data would be sitting in 1 dimension, and in the other dimension, the 2 classes would be separated. So this would be part of the goal of topological data analysis and manifold learning, which would whose hope is to identify these manifolds on which the data lives. However, it's not clear that once you reduce the data to these low-dimensional manifolds, whether symmetries become simple. So, for example, suppose that here in this spiral example, you have a translational symmetry on the spiral. If you move on it, you stay within one class. If you move orthogonal to it, you have another one. Now, the distance function, the distance between adjacent points and how similar two different points are, it is not guaranteed that once you train a classifier to classify these two classes, it's not guaranteed that it also learns this distance function nicely so that, you know, a meter, let's say a centimeter on this side is the same as a centimeter on the other side in terms of similarities between data. So if you check the correlation between two data points that are 1 centimeter apart here, it's not necessarily the same as the correlation 1 centimeter on the other side. So in that sense, it's the, you know, finding the low-dimensional manifolds on which the data lives doesn't necessarily make finding the symmetries easy. However, you can use it as a next step. You can have an extra step to enforce, to say, okay, I want to have this kind of translational symmetry here. Can you find it? And it's certainly going to be easier once you go to this simpler representation of the data in this low-dimensional space compared to the original representation of the data. Yeah. But I think this is one of the problems that I would also like to think about some point later. How do you look for symmetries in the embedding space of some data set? Because most of the work that is currently been done in encoding symmetries into neural networks, it works in the original representation of the data and assumes that a simple group transformation that we can somehow encode into the system, into your architecture, exists, basically a simple group transformation. Oh, and when I say group, I mean a simple transformation that's a symmetry of the system. They assume that the symmetries have simple representations in the original form that the data is presented to you. And one of the works that we did, that was the NeurIPS paper last year, we were trying to develop a simple method to be able to find symmetries if they exist in the system. And our method doesn't necessarily rely on the symmetries having a simple form. So they can be complicated. For example, let's say you might have a rotation symmetry in some data, but the data is presented to you in a jumbled way. Let's say you have rotations in your images, but your images are scrambled, but they're scrambled in a fixed way. The nodes have been, the pixels have been moved around. So when a person looks at it, it's very hard to see that there could be any like rotational symmetries in this system. However, our method doesn't care about such scrambling. So essentially, it does just as well on the unscrambled data versus like the scrambled data in terms of finding the symmetries.
Very interesting. So back on that, because what you said earlier, like I talked about how embedding learning, representation learning, in a lot of cases is essentially manifold transformations that keep the symmetry. They don't necessarily know what the symmetry is. The power of deep learning architectures are that they learn how to go to a lower dimensional space and reduce the redundancy in the original the manifold that data was on, without losing the important symmetries. But I think the caveat was that the architecture should be able to preserve the original important symmetry, right? A good counterexample for that, and related to the question that Serena asked about, data visualization, like we use convolutional neural networks very frequently. And you taught me recently that, that like the reason the convolutional neural networks work is that images in general have, or the way we translational symmetry. Like the way we extract information from this corner of the image is very similar to how we extract it from here, right? So that translational symmetry. Now, like you're saying, is that what if the image is not, straight, like it is sometimes rotated? So that translational symmetry, so using CNN like this is not going to perform as well. So the research that you've done is essentially, how does CNN need to change to also understand, this new nuance, which is, the image, yes, it has translational image symmetry with this particular assumption that all the images are upright. But what if a bunch of images in random ways? Is that the objective of what you try to do in your work?
Yes, and I should clarify, I mean, there was a whole line of work started many years ago, but especially gained steam since like 2016, where people started trying to generalize convolutional neural networks to systems that can encode more symmetries. And one more clarification about what we mean when we say like images have translation symmetry. We don't mean that, your face is repeated like 10 times, with shifts inside the same image. What we mean is that in the data set, you expect the distribution of where the features appear to have this symmetry, meaning that if you see a cat image on the left-hand side of the image, you expect there to be some other data point inside your data set where the cat image is, shifted somewhere to the right. So in that sense, there is that symmetry. And then the rotation symmetry that you're talking about, yes, you can have, for example, the cat's face might have rotated. What the CNN does is it says, I'm going to look for the same cat face if it is shifted anywhere in the image. But then if the cat face had been turned slightly, the filter that the CNN tries to match to different patches of the image do not match the rotated. They match the shifted versions, but they don't match the rotated face of the cat. So it means that that old filter, which might have worked perfectly well for identifying a cat, doesn't work on the rotated version of the cat. So now you need to have a more generalized CNN that also rotates the filters and tries to match them. And that way, with fewer filters, you can match more patterns, basically, symmetric transformations of the same pattern.
So it sounds like an advantage is in simplifying or making the architecture of a CNN more efficient by sort of injecting the ability to handle symmetries. Is there also an implication on the embeddings? So let's say, like, I'm not even sure because I don't do much computer vision, but my assumption right now is that if you have an image of a cat and you flip that image of the cat, you put that into some vanilla CNN, I think the embeddings may be slightly different and would not map to each other one-to-one or collide. Would the ideal goal be for a CNN to actually output two embeddings that are extremely close if they are just, I guess, rotations of each other in terms of the input images?
Yes, but not just that they are close to each other. Rather, the goal is to basically the same cat filter, for example, should give a positive response to both the unrotated and the rotated version. It should not put them close to each other, though. So let me also clarify this other point about what these symmetry-preserving architectures try to do. let me take one step back and I'll come back to this. So one thing that Amir mentioned is that you want your architecture to preserve the symmetries. Unfortunately, they don't. So that's the goal of these new types of architectures that we're working on, is to make architectures that respect the symmetry in a particular way. These architectures are generally called group equivariant neural networks. And equivariance is a kind of a new word and difficult to remember, but essentially what it means is if you do a transformation on the input, you want some version of the transformation to appear in the output. So equal to that variance that you did to the variation that you did to your image. You want the system to be equivariant, meaning that if you transform the input, some transformation goes to the output. Now, a CNN is equivariant under translations. What does that mean? It means that if I give it an image with a cat on the left-hand side, if it has a cat filter, in the output, it gives you an image again, but its cat filter is activated on the left side. If you now move the cat image to the right, it gives you an image that the cat filter is activated on the right-hand side. Now, when we say that CNN is not equivariant under rotation, it means that if you rotate the cat image, now suddenly the output image with the cat filter is not activated at all. The thing that you said about embedding, Serena, in an equivariant neural network, the embedding that you get from the neural network will have a version of the symmetry present in there. Meaning that if you now start rotating the cat images, in the output, it will show you that basically in the rotation space, the cat filter has been activated, but in the rotation space, it has moved in the direction of increasing angles. So there's a whole interesting math story there, but it would be maybe too much to discuss right here. Yeah.
On the topic of math, I want to acknowledge a few questions and I guess in the YouTube chat. So Sergey says that at some field theory textbooks, and
right,
is very frequently used there.
Yeah.
And yes, definitely. As we said, we love symmetries in physics. And well, I mean, they teach just symmetry for the majority of the courses that at least I've been exposed to.
Yeah. Go ahead. I definitely have some things to say about how important it is. Yes.
Go for it then.
So, I mean, what I wanted to mention, just the quote that Serena mentioned from Phil Anderson saying that basically physics is mostly the study of symmetries, which also Michael Bronstein, who is one of the main people in graph neural networks and equivariant neural networks, also said that in his iClear 2021 keynote. In physics, all of the forces, all the fundamental forces of nature are actually symmetries. They are consequences of localized symmetries. It's a little bit hard to describe, but in physics, we call that gauge symmetry. It's, a whole different story. But essentially, the way you can think of all of the forces in physics is how a pattern of symmetry in one point changes when you go to another point in space. And it includes electromagnetism, it includes strong and weak nuclear forces, as well as Einstein's general relativity for theory of gravitation. Yeah, and so go ahead.
Yeah. I had not heard the term gauge symmetry for many years. Thanks for it. Just feels so good. The second thread of conversation in the YouTube chat is Manish Singh, which I on some related work. He's sharing a lot of resources and thoughts with us, and I'm adding some of those to the recipe we are going to share for the session. But I'm going to ask Manish, please reach out to me because I would love to see a few more resources on this topic, and we can add it to the, but also essentially maybe bring you this show in a future session. On the topic of recipe quickly on the screen, and I'm going to ask Serena and Nima to quickly say what's your favorite resource that we have on this recipe and what should people definitely take a look at. So while you click that and get to answer, I'll just share my screen quickly. So the link to this is in the YouTube video description. So you can click on it and see what I'm looking at right now. But my favorite one is this video that you're talking. I'm kidding. But Nima, was this? Which one was your paper? This one is your paper, isn't it?
The automatic symmetry discovery.
Yeah.
Yes. This one. Mm-hmm.
Yeah. So is that your favorite resource on this recipe?
No, actually.
Oh.
I mean, because our paper is very technical, and it tries to tackle a problem that you only realize after reading a lot of the other literature. The problem that we tried to tackle here was that people started making new architectures that would encode different types of symmetries. But for every new type of symmetry, they were building a new type of architecture. And the way they were building many of these architectures was there were two different routes. The simple route to explain is, for example, for encoding rotation symmetry, they were saying, I'm going to create something just like a CNN, but it's going to rotate the filter by a lot of small angles. And so basically they were sampling the whole space of transformations, like in this case, just all the angles, by some discrete amount. So first of all, the discretization is introducing some error into your approximation. And secondly, it's tedious and difficult for large groups. So for example, for a 3D rotation, you have a lot of different angles that you need to sample in order to have a good representation of this group. And what we were doing here was trying to introduce a very simple architecture that we show can approximate any of those existing architectures, but also is simple enough that it could potentially allow us to learn what the symmetry group is. Because in all that I described so far, the way people built the architectures was they assumed some symmetry transformation, a specific symmetry transformation existed in the data, and then they would go and encode that symmetry. But in physics, a lot of times we discover new symmetries in the system. Like we had no idea that the strong force has an SU3 symmetry, which is like some complex matrices with 3x3 matrices. So we wanted to have a method that allows us to do such things, to look at data where we have no idea that a particular symmetry exists, and yet this structure would be simple enough for it to be able to deduce the existence of certain symmetries.
Very interesting.
So I would suggest actually reading some of the first I think the let me see, the group equivariant convolutional networks. That was one of the earliest papers in this, basically number 5 in the recipe. I think that's a good resource for giving an idea to like what the reasoning is and how people early on thought about this. And then the review, the geometric deep learning review by Michael Bronstein and Petar Velechkovich, which I don't see here right now.
Yeah, I probably haven't added that yet, but I will add it after this session. Serena, how about you?
Yeah, and it's number 5 as well for me, the group equivariant convolutional neural network, simply because I think Nima is the one who added that resource in our shared notes and wrote that it's one of the seminal papers. So if Nima says so, it must be important. And
I
yeah,
mean, it's not necessarily.
yeah,
Mhm,
go
go
ahead.
ahead.
Yeah.
No, I was saying it's not necessarily the best paper in the field, but it's just, one of the earliest papers that gives you an idea about how people started thinking about encoding symmetries in the system, in the neural network architecture again. And then you can look at a lot of the papers that followed them, especially the two authors on that paper, Taco Cohen and Max Welling, are some of the leading figures in this whole line of research. And Taco's whole PhD was, a lot of papers on this topic.
Hmm.
Uh, so I definitely recommend looking at more of the work in that direction.
That's awesome. Yeah, so I would maybe ask Taco this question and also Nima. So, as an industry practitioner of machine learning, I would wonder, why do we care about symmetry once again? So I can understand that it can, or have using networks that understand symmetry can decrease the number of parameters we need for our models. And I'm also thinking about data augmentation, or let's say like data reduction, because when I
Yeah.
learned about convolutional neural networks, I remember reading that it's often suggested make various copies of your input images, like spin them around, rotate them, change the color, and that's a lot of data augmentation. So now I'm wondering, if we have neural networks that can handle symmetries, would we not need to do this exercise of
That, that's
augmentation?
so that's yeah, so that's the hope. And I have a couple of things to say about what you just mentioned. But the first about data augmentation is, when you talk about images, it's easy to think about augmentation because we are familiar with the real world and what the space is that where these images come from. So we have a good prior for like a good assumption on what would be a good transformation that is likely to be a symmetry of the data set. Meaning, if you see a cat, it's natural to see some rotated image of the cat as well. So because we know so much about this space, it's easy to guess what a good augmentation method is. If you go to an unknown world, or like, you're analyzing some complicated space of chemicals in quantum chemistry, or like, in physics problems, a lot of times we don't know. We want to discover some of these symmetries. So there, you're not allowed to do such augmentation because you are inducing a bias into your system by adding these particular transformed versions of your data into the system. And now, one other thing I wanted to say about well, practitioners, why they should care. There has been this debate recently, maybe a lot of you saw this on Twitter, that some of the big shots in the field are saying the game is over. And what do they mean? A lot of them say that language models are the ultimate, route to uh, general AI, and basically they also say we don't need any new theory. We just need to scale up. We just need to make things bigger and bigger. I do not agree with that assessment, but I cannot articulate all of my uh, complaints about it right now. However, one of the leading figures in scientific AI, Anima, I forgot her last name. She's a professor, I think, in Caltech, and she works in mostly in fluid dynamics, but I think now she's also working on quantum chemistry and so on. She had a tweet, I think, this morning, uh, about why we still need theory, and saying that the space of possibilities, I think she was saying, for example, the space of possible configurations for a chemical in a quantum chemistry problem is so large that it would take the age of the universe with like so many like, all the compute resources that we have in order to compute and sift through that. And what symmetry equivariant neural networks allow us to do is to reduce that space drastically and actually make the computations tractable. So in industry, especially the ones that are working with scientific problems, there is often this bottleneck with data and the vast amount of search space that they have to go through. So I think there's still a lot of value to be gained from doing theory like this.
Yeah, to me, answer to that question has two aspects. One is, observing that mindset of, oh, I'll throw more data at it, is sort of a bit from how the latest AI revolution happened, where there was more compute power available, more data available than ever, and all of, oh my God, let's bigger models. But at some point we are going to start asking questions. Wait, what does that mean for the environment? Like all these GPUs, the power consumption, et cetera, the generalizability, the access. Who can train these models and use them, right? So there are a lot of tangential questions that have to be asked. In addition to the fact that very few organizations that have access to the amount of data that is plausible to even do anything interesting. So this whole newer motion around data-centric, machine learning response to that. Okay, so let's calm down for a while, great, but let's understand what we are doing. Like, let's actually look at our data and see if we can create models that generalize better, train better with smaller amounts of data. Let's try to optimize the outcome, not with, throwing more data at it or making the model better by, manipulating the input data in a specific way. So I think that's one important aspect why symmetry is important, because if you understand the symmetries in input data, then you can build it into the model so that the model learns those rather than trying to just examples and hope that eventually we'll figure those things out. So that's what the other one is. Nima said, scientific applications, and Manish also mentioned in the YouTube chat, saying the real world is based on symmetries. So any application of machine learning applied to real world things, like all the physics inspirations of machine learning, fluid motions, and climate change, and all of these real world things that involve some level of physics, domain knowledge. We have so much knowledge that are based on how symmetries are leveraged. The nature, the physical systems, and all of that knowledge will be completely want to rely on the architectures that we have. We have to build systems so that these systems can be trained with much less data in much more reliable ways.
Yeah.
And another another argument for decreasing this, or updating models so that they're able to handle smaller training data sets and still have optimal results. At Shopify recently, I'm part of the machine learning ethics committee there, and we were looking at the dangers of large pre-trained models. And Nima, you really made me think about this when you said that these pundits on Twitter say, we're done, let's just make the models bigger. Well, one interesting stat is that ImageNet, so the ImageNet data set, has 0 consensual images in it, and it actually has non-consensual images of children. So wouldn't that be great if we could train CNNs that don't need all of these non-consensual images? And then there was also another interesting thing I learned recently, which is that the larger the language model, actually the easier it is to perform training data extraction attacks. So what that is you can get the GPT-3 API, query it 100 times, and using some sort of measure of perplexity, so NLP metrics, you're actually able to extract data from the training set, which is pretty scary.
Yeah, I've heard that, and I saw some examples of it on Twitter. But there's also a lot of curation that goes into training these models right now. So I'm, it's so opaque. They put out DALL-E or like Imagine, and they say something about the architecture, but there's so little said about the curation of the data that I honestly don't know, really. I don't have a good picture of what is going on there in the back end. I also haven't used transformers myself because I don't understand them theoretically yet. So I do want to, spend some time trying to work it out and figure out how they work. Yeah, but there is these problems with going to scale that, to be honest, concerns me a little bit, because it feels like we're doing something very big, very fast without really knowing what we're doing.
Yep.
I also wanted to say something. I feel like what you said, Amir, is also very valuable about what you said about all this knowledge that we've accumulated in physics. Suddenly, it made me think of the Apollo computer, essentially, like where, without basically the whole computer's interface with humans was like 4 numbers that it would show, or like 3 numbers that they had to go and interpret and see what the message is and what to do with it. And it feels to me physics is kind of like that Apollo computer there, where with very little resources, with very few parameters, people achieve so much, with the just scientific method and simple principles of beauty and simplicity in your model building. We managed to build models that, can explain most of what we see out there in the universe, and that's amazing. And I think, yeah, it would be a waste not to learn from that and not to try to incorporate some of that. My personal opinion is physics needs a bit of big change in terms of how they're viewing problems and what their methodologies are that they're focusing on. And there are a lot of people, including Kyle Cranmer and some other physicists from like LHC and so on, who are working a lot on bringing machine learning into physics modeling and just physics in general. I hope that grows. I also feel there are a lot of similarities in what physicists have been doing, which was looking at data, interpreting it, and building predictive models, and what machine learning people are doing. So I do feel that these two groups need to come closer and then, exchange tools more.
For sure. The very first time that I went back to my PhD supervisor and told him that I'm a data scientist now, his reaction was, "What have you been so far?" Him referring to the fact that I collected probably 6 of data for my PhD and then analyzed it to write the paper I did. So definitely get that, and 100%. We are unfortunately out of time. We are at the top of the hour. So Serena and Nima, what are your 30-second wrap up, verdict, and call to action?
Yeah, that the power to do data set reduction and also reduction and simplification of models seems potentially very powerful. And I'm excited for when there's a scikit-learn implementation of Nima's work or other researchers' work.
All right, Nima?
Do more theory.
That topic, we should definitely do a session to do a debate, a scientist and a physicist. I had my previous work, who was really into philosophy and came from computer science background, and we about how computer scientists see the world and how physicists see the world, and it is drastically different. Is well, I have an opinion about which one is better than better, but definitely a lot of interesting things to cross. Nima said, definitely we've been doing, physicists have been doing things in certain ways for centuries. There's some merit in it, and of course we have to learn from more statistical ways that computer scientists are looking at things.
But if I may add just one last thing, is that physics was part of the rest of the sciences which relied on the scientific method, which was a reliable protocol that we came up with in order to establish some mechanistic understanding of the world. And I feel machine learning, what we do is chunks of the scientific method. You have some fitting parts, and then you have some generative part, but they're oftentimes disjoint. I think we need to also think about how to have a more rigorously scientific protocol for certain machine learning problems that would be science related.
Or computer science in general. Thank you so much for joining us today. Next week, we are having a very, well, I guess, famous guest. I will, check out our Slack and social media for announcements about it. We are still finalizing the details of the topic, but I'm sure you're going to be very excited when you hear about him showing up on this show. So make sure you subscribe to this channel and come back for more shows. Thank you so much. We'll see you next week.
Thanks, everyone.